But if you then extrapolate into the future, and these are these three scenarios I mentioned yesterday, when the Intergovernmental Panel on Climate Change was trying to predict what would happen to the planet. You could have, well, they now use a number of different scenarios, but in the early days they used three, that we either have business as usual, where we let the world go on with its business and emissions continue to increase, or we can really seriously do something and reduce emissions, or we can really deliberately stimulate more emissions, do a Trump, and let's burn as much coal as we can get hold of. And so the top one, the bottom one here is the Trump approach. The middle one is business as usual, and the top one is sort of virtue. So business as usual is the most likely, and we can see that the fact that the Arctic is warming faster than the rest of the world means that by the year 2000, the Arctic will be this is about 7 or 8 degrees warmer than it is now, while the rest of the world will be about 4 degrees warmer, which itself is disastrous. I mean, if the whole world warms by 4 degrees, then that'll be a sort of catastrophe. But the Arctic will be twice as warm by twice as much, and that'll mean a vast amount of ice melt, causing global sea level rise. So that's what the predictions are, based on the fact that we have this Arctic amplification going on. We're going to get a very, very warm Arctic in the next few decades. Well, and a very, very warm planet, but the Arctic will be warmer still. Then what does that mean for the ice as well? It means that the ice that I showed at the beginning, the big solid ice flows, aren't there anymore, because nearly all the ice now in the Arctic melts in the summer and then forms again in the winter. So it's called first-year ice, which is like the ice you get in the Antarctic. Whereas in the past, it would sit there or drift around, but get thicker every winter. So when you went out on it, you were really dealing with a very formidable landscape. This is what multi-year ice used to look like north of Alaska, and this is in summer, in fact. So this water you see here is meltwater, which has melted off the top, but it's still sitting there and will freeze again in the autumn. So it's like the Grand Canyon bit, and it's very formidable ice. It's lost most of its salt. It's really heavy ice. You can't break through that, where you could just about break through it with a Russian nuclear icebreaker, but not with anything else. And that's the way the Arctic looked when I was young, and I used to work up there. This was really exciting to go and work in this kind of landscape. It was that multi-year ice was very formidable, exciting stuff to work on and drill holes in and study. But now there's scarcely any multi-year ice left in the Arctic, and this is what well, the background picture here is what the Arctic now looks like in the winter. It's called first-year ice. It's very thin, and it's formed that year and melts again in the summer. So it's weak, it's thin, it doesn't have these big rugged ridges in it. It looks really a bit pathetic, and it is quite dangerous to work on. And this is the amount of multi-year ice. It was only in the last 15 years or so that multi-year ice disappeared. So before the year 2000, you had that kind of dramatic landscape that I showed first of all, and then the amount of multi-year just went right down during the 2000s. And there's a satellite which can detect the difference between multi-year ice and first-year ice. So the red is multi-year, and multi-year ice used to dominate the Arctic, and that's the way things still were in 2004. And then each year since then, the amount of multi-year ice has decreased, and I've got a more recent one here. I'm not sure which, oh, here we are. This was 2012, and the multi-year ice is red, and there's just a little fringe of it across the north of Greenland. That's all the multi-year ice that's left in the Arctic. Well, the blue is a little bit of elsewhere, but mostly is gone. And so we've now got this thin first-year ice cover like you have in the Antarctic. Okay. So that was the extent, and it was of course you can't avoid detecting that the ice is decreasing in area. But what the scientists and the modelers didn't realise was it's also getting thinner. I mean, you would expect maybe that if it's decreasing in area, it must be getting thinner as well, but they didn't sort of connect that. And so the measurements of how thick the ice is more difficult than the area. The area you see from a satellite, but to measure the thickness, you have to go underneath and then use an echo sounder looking upwards to tell you where the bottom of the ice is. So that work was done from submarines. So for the last few decades, we've needed scientific use of nuclear submarines to tell us how thick the ice is in the Arctic Ocean. There hasn't been a satellite that can tell you ice thickness, only area. And there still isn't. In fact, there is a satellite, but it's not generally regarded as giving very reliable results. So we still need to go underneath the ice and look up to measure the thickness. So the two countries that have done that work have been United States and Britain, and Russia's done it, but it's never published any results. So I got involved with the British end of this right from the start of the first British submarine in the Arctic. So I've been going up there with Royal Navy submarines measuring ice thickness for 40 years now, and it's been a very, very fruitful thing to be able to do, and a great privilege to be able to sail on a submarine. At least it was until we had a fatal accident, but it's otherwise it's very useful. So this was the first trip I was on, and this shows the submarine, the Sovereign, surfaced at the North Pole, and so this is the whoops. But the reason I wanted to show it is just that's how you did things then, and you still do them the same way. And but the first surprise when you go under the ice and look up is just how rugged the bottom of the ice is. You see these landscapes of ice and you sort of think, well, it's fairly rough, but you can see it's basically a flattish landscape. But underneath you have this network of pressure ridges which are very, very deep. This well, quite deep. This one is 40 meters deep, and we've measured pressure ridges up to 50 meters deep, and they're caused by the ice opening up because of the wind causing ice flows to move apart, and then new ice grows in the gaps. Then the wind closes the ice up and pushes it down under the surface of the sea, and it piles up a ridge. It's like a kind of slag heap, but a linear slag heap of blocks of broken up ice, which freeze together and give you a really formidable obstacle. So this is, oops, here's a series of pressure ridges showing you how deep they are, and then the flat bits are they're not very flat, but they're the undeformed multi-year ice, and then the thinner stuff is first-year ice and leads that are refrozen. So we can see the whole under ice landscape here of undeformed ice that's fairly flat, the ridged ice which is really formidable ridges, and about half the ice is in the form of ridges. So immediately you have to start profiling this. You've got to measure the distribution of thickness, the numbers of ridges, how deep they are. You immediately have a job to measure everything here and then try to understand and model why the ice produces this kind of appearance. So that was what I was busy doing for many years. But eventually I noticed that we were sailing over the same terrain in successive voyages. And in fact, I got the submarine to follow the same tracks as it had followed on an earlier voyage. And so for the first time we were able to see how the Arctic ice had changed over an interval. And in this case, the interval was 11 years. And so we had one data set from 1976 and one from 1987. And this was 1976 on the left-hand side. These are contours of ice thickness. And we can see that it got pretty thick north of Greenland, 5, 6, 7 meters. And the rest of the Arctic, this area of the Arctic, was about 4 meters thick. Then in 1987, we were surprised to find that where it used to be 4, 5, 6, 7 meters, it was down to about 4 meters, 4 to 5 meters. So that big change happened between there and there. And then, so I published that in Nature in 1990, and that was the first paper on ice thinning in the Arctic, and that showed a decrease of 15% in ice thickness between those over that 11-year period. But then when you keep on looking, you find in 2004, for instance, that's this top right-hand curve, that the area north of Greenland, instead of being 7 meters going down to 4 meters, is down to 2 meters, 2 to 3 meters. That's that much lower thickness. So the thinning has carried on happening, and there we are. That's an interlude to show you what life is like on a submarine if you're a civilian. If you're a civilian, you get to sleep in a torpedo tube rack. So I was with, this is my colleague from Cambridge, and showing our home, which is, they clip a bunk to a rack, the torpedo rack, where there isn't a torpedo, and you get to sleep there. Of course, when you wake up in the morning, as soon as you lift your head, you bang yourself against some metal thing, and so you always end up with a mass of bruises. And when they have exercises loading the torpedoes and unloading them, you have to go and hide in case, so you don't get loaded yourself. And then you've got these missiles as well. You're trying to sort of save the world by measuring the ice thickness changes, but the captain is trying to sort of practice making war. So it's a kind of slightly bizarre world where, as a civilian on a submarine. And then this was the most recent voyage that I did, which was 10 years ago now. The reason was we had an accident on board and there were 2 sailors killed. We were doing, for the first time, I was putting a multi-beam sonar on the bow of the submarine, which actually measures gives you a kind of 3D map of the underside of the ice. Instead of just a profile, you have a nice map and you can see the ridges. So it's really very, very nice, improved way of measuring the bottom of the ice. And so it was really the best voyage I'd ever done on a submarine, but unfortunately it was the last one because the British Navy stopped sending submarines to the Arctic at that point. There was an explosion on board from a faulty oxygen generator, and 2 sailors were killed. We were under the ice, the submarine caught fire. It was pretty gruesome. I was expecting to die any minute, but we managed to surface and get everybody out. And so it was very nasty. It was a human failure, as usual, that they reloaded faulty oxygen generators, which they'd sent back, and the parts department in the naval base had said they must use them anyway, even if they were faulty, because they wanted to save money. So that led to 2 people's deaths. Anyway, this is just another scene. If you want to take some pictures along and hang them on the wall, you can't, because there isn't any wall to hang pictures on. This is every square inch on the submarines has got some instrument or pipe or something. And the other useful thing that you can do as far as properties of ice are concerned is that they'll not only do they take the submarine where you want to go, but they'll also put you ashore, or put you on the ice, and then you can measure the forces involved when the submarine breaks through the ice. So here they put us on an ice floe, went underneath in some fairly thin ice in a lead, and then surfaced, so we were able to measure the forces that it exerted on the ice. So here it's just breaking surface, and then then here it is emerging at the bow and the fin, and then there it is up, and because then they took us back on board again, so they had to do it in the right place, otherwise we'd be marooned in the middle of the Arctic forever. And this is sort of data that it collected, and it's very high quality, and it shows you, in this case, a pressure ridge. Instead of just seeing that thing like a triangle, you can see the whole shape of it, and how long it is, how it interacts with the next pressure ridge, and so on. So it's a marvelous. We're still working out what the data means. So there we were doing that, and that's what's been providing the information on the thinning of the ice. And a typical submarine voyage would take you right across the Arctic, so you sample the ice around Greenland and in the north near the pole and in the Beaufort Sea. So in fact, in that case, the place where we had the accident was just north of Prudhoe Bay. Okay, well, the first thing you find when you look at all these ridges is that the yellow ones here are the multi-year ice, and the purple is the first-year ice. So the multi-year ice has these big, deep pressure ridges, but the first-year ice, this thin stuff we now have, has got a lot fewer ridges. And so we've carried on, because we had to give up using submarines, and we've carried on doing this with autonomous vehicles called AUVs, which do the same job, but they don't have a person on board. You program them to sail under the ice, do a crisscross pattern, and then come back up. And there's a lot of technical problems involved in getting it to come back where it started from, and you don't get such a long distance track either. So it's a hell of a lot of effort for much less data than sitting in comfort in your submarine, but at least you're not there under the ice. And this shows us some of the scenes of doing this. That was okay. This is you cut a hole in the floor of your tent, put the vehicle through, and we were measuring this pressure ridge on the right there, and the red and black tent in the background is where we launched the vehicle from. Then this is showing in another part of the Arctic building our own camp. So we went out from a Canadian base out onto the ice with all this stuff, built our own camp, and built another tent to live in. This is the hole in the floor. And so there's all this effort required to get about a tenth as much data as the submarine used to get. So I'm not a fan of AUVs. I'd rather be back on submarines, but they have to make them safer first. And this is that pressure ridge, and we can see the detail that using an unmanned vehicle, you can get closer to the ice because you don't have to worry about hitting it. And so here's the very high quality picture of the bottom of the ice. And in fact, you can see how good the quality is because the red circle shows these very tiny individual blocks in the ridge. And then we had a diver go down to that spot and he could see those blocks. That's on the right-hand side. So you can see that it was really showing what was there. Then this is another part of the Arctic also with an AUV with a multi-year flow, and that's a multi-year ridge, and you can see more formidable sort of structure there, bigger blocks that would be much harder to break through. But you take all that data from those subs and the American subs and add it into the extent data, and we get a volume. The extent, we know the area is... we know the area, but now we know the thickness as well, which is also decreasing. You multiply the two together, you get the volume, and it's really going down. And so in 2011, the volume of the ice in summer was only a quarter of what it was in 1979. So in summer Arctic ice, you look at the Arctic Ocean in summer, there's only a quarter as much ice as there was only 30 years ago. So that's a massive change in a part of the planet. And the way that's been expressed recently was a thing called the Arctic death spiral, which this was at Boulder in University of Boulder University, the University of Colorado. They came up with, what they did was to have a clock pitch curve where the distance from the centre is the volume of ice for a given month of the year, and you start off in 1979, you come round to the present day. And the black line is September, and the green is winter months. So September is the nearest to the centre, which means the least ice. And if there was no change going on in the Arctic, then this would just be a series of concentric circles. But because the ice is disappearing at all seasons of the year, each of these curves is coming in towards the centre, so it's forming a spiral. And the first one to reach the centre will be September, and then there will be August and October will follow quite quickly afterwards. Then the rest of the months will last longer. We don't know how long, but eventually all the ice will disappear. But that's the death spiral, which is, I think, a very good graphic way of showing the seriousness of what's going on. You can extract September alone, just look at that, and we can see that's heading down exponentially towards zero. And this shows it reaching zero in 2017, which it didn't manage to do, but there's wiggles on that, so this is 2016. This is from my book, and this is just looking at the ice area in summer, or coming down towards summer and then back up towards autumn. And the bottom line, the red line is 2012, which was the record. But then 2016, which is the black line, you can see through most of the year that was a record low for the time of year. But when we went on to summer, it just nicked the bottom of the curve here, and it didn't quite reach the 2012 record. But for most of the year, the 2016 was the lowest area of any time.